Thank you for being here. This is the NG Firewall Clustering Deep Dive. I got to turn around, make sure it's the right deck. Once I was presenting in the US a few years ago, and we didn't have any monitors in front of me, so I just facing the audience and presenting, and I click into the slides because I remember it pretty well. Turn around, it's some call manager image on there, and nobody said a word for the first couple of minutes. So I always turn around, make sure I'm talking to the right deck. So my name is Andrew Osipov. I'm the principal engineer with the Cisco Security Business Group. So what I do is mainly network security strategy, new feature development, kind of figuring out where our portfolio needs to go to make you all feel very happy. I also dabble in things like innovation, so I sit on the Cisco Security Patent Committee. I participate at IETF in TLS, Transport Layer Security, and Service Function Chaining working groups. And beyond I like talking to customers. So why people ask me why you go and present at Cisco Live. So to me, the benefit is twofold. First of all, I really enjoy talking about things I work on, sharing the latest and greatest ideas and our plans with you, taking your feedback. That's the second most important. That's actually the first most important part, taking your feedback and making sure that we are developing our products and architectures according to what you want and need. And in fact, a living example, many features we're going to be talking about today came straight from conversations with folks like yourselves. There'll be features, for instance, a good example, last year at Cisco Live Orlando, we sat down, I had a conversation with a clustering customer and had a very particular problem with overlay transport virtualization, and we could solve that from the clustering perspective, and so we did, and that feature is shipping this spring with the next ASA release. So that's a pretty good turnaround in my book for something that we just dreamed up at a Cisco Live, or after a Cisco Live session that we put straight into the product. I'm very open to answering questions, obviously here, but also you see my email address up there. If you ever have a question or follow up to something we talked about, feel free to drop me a note. I'm pretty good usually at answering email, and I keep those sometimes, customers from many years prior, they shoot me a note asking a question, and I'm always happy to reply back and have that chat. We also have this Cisco WebEx Teams room, which you have to download the Cisco WebEx app, and there is a WebEx Teams app, and there is a link in the event app and in the presentation description where you can join and ask questions. Now, I don't have anybody else but me answering those. I believe if I tell you something and you have a question, I owe you a response directly. So I won't be answering during the session, obviously, because I'm speaking, but right after, I will make sure that every one of your questions will be addressed in there. On the agenda today, when I say deep dive, I mean a deep dive. I don't pause for breaks, a little joke. Well, sometimes maybe I'll throw a little joke, but I don't pause. I just go and deliver you content. So it's a pretty deep dive into our clustering technology. I'm a little bit proud to talk about that. It was one of my original projects at Cisco, one of the things that I helped architect and continue to develop features like, for instance, inter-site clustering. Recently we shipped ACI, Anycast Services Gateway, together with the ACI business unit. That was also something we co-architected. By the way, I believe there is somebody in the room who talked to Fabian Gandola, and he promised you I'll have a deep dive into ACI multipod. He lied. I will talk a little bit about ACI multipod. If you still have questions, please see me after the session, and I will definitely point you to a very detailed deck on ACI multipod with Anycast Services Gateway, and make sure that you are you're good on your implementation. So without further ado, let's kind of talk a little bit about what clustering is, how it comes together. And let's start that by talking about ASA failover, or FTD high availability. I like to build on a very well-known concept. How many of you deploy failover or deployed failover in ASA? Okay, very nice, so quite a few of you. So what are the good things about failover? Well, first of all, something I personally like is that you have a single IP and MAC address for your first hop routing. So if you have a failover event, that IP address, MAC address, they move, and you don't really see a disruption at the network level. And there are different things like stateful connection synchronization, so you pick up where you left off. There is configuration replication, all those good things. But one thing that often goes overlooked, and that's specifically something we saw when we did high availability on FTD, when we looked at the Satisfier product, which never had that capability, there was stacking and clustering, a different kind of clustering. But it was not a simple thing like an active standby, where you have two boxes, one is active, one is standby. And the biggest thing in a stateful inspection world is you really want to see all packets for a single connection on a single device. So when something crosses your network in a certain way and crosses one firewall, you don't want the return traffic to hit a different firewall. You want the symmetry. So that's what active standby does. Since only one box is active, the second path is disabled, so you don't have that situation where packets for one connection go through two different paths and create that disparity in a stateful record. But I would argue that it's not really what I call a symmetry normalization. It's really a symmetry avoidance. Yeah, you have two boxes and you disabled one and you don't actually get the benefit of that second box. So what does clustering do for you? So clustering allows you to take up to 16 individual modules or appliances and bundle them into one big logical firewall. And that's just the simplest way to look at it. Imagine that we just stacked a bunch of firewalls and made them look like one big device. So what do we carry forward from failover? Yes, you still have a single IP address and single MAC address for first hop redundancy. You still replicate the connection state, so if something fails in the cluster, you pick up where you left off. But the biggest benefit of clustering, beyond this distributed processing and scaling connections and throughput and such, is the asymmetry normalization. So that gives you true scalability. And how does it happen? Well, if, like I said, you have a leg of a connection which crosses a particular cluster member, the most important thing is to make sure the response goes back through the same unit. So clustering gives you that. So even though you have 16 boxes, and every single one of them is capable of picking up a packet and processing it to completion, you still make sure, we make sure for you that even though your load balancing is stateless to the cluster, that all packets for a single connection go to one unit, so you get the complete stateful view of what's happening with this connection. So that's the biggest benefit of clustering. What do you need to get started with clustering? So if you look at the classic ASA appliances, 5500X, and 5585, we support up to 16 on the 5585X. The licensing has to match. There are some minor requirements like that. But when you look at the new firepower appliances and look specifically at the ASA application, yes, same idea. 4100, 9300, 2100, it's coming. I know it hasn't made it there yet, but we started that process of getting it on the 2100. So you still can do up to 16 modules or appliances running ASA in a single cluster. Now, FTD is a bit of a special case. Now, when we shipped FTD clustering, we only tested with up to 6 modules or 6 appliances in the cluster. Why? Well, back when we did it, you needed a pretty beefy traffic generator to generate so much application and thread traffic. We didn't have a big enough appliance. There wasn't something on the market that would go beyond like 200-300 gigabit of pure application traffic. So it took us a little bit of time to not only procure that hardware, but also to get to doing that test. So prior to FTD 6.4, which is shipping in April, you would look at the documentation and you would see up to 6 modules. However, we actually allow you up to 16, and many customers did that. It's just that's not something we documented. So I'm happy to say in 6.4, we are going to officially support up to 16 modules on both ASA and FTD. Now, in the past years, if you ever attended this session or look at the recording, I'll give you a little speech about the explicit switch support. Here's the list of switches which we support with clustering. And I never really liked this requirement. I don't know, I always did a show of hands, and many of you said, you know what, I have this switch, we have a newer version of this switch, I just don't want to I don't want to replace that switch and get something on your list. So we pushed for supporting a generic switch, and we made it happen. So as of about a year ago, I think it's a ASA 9.8, 9.7 or 9.8, and the corresponding FTD release, we no longer require you to have a particular switch to connect the cluster. It could be any switch. We documented the requirements from the switch in the configuration guide, and they aren't anything special, right? You got to support standard-based LACP. You shouldn't drop frames unnecessarily. You should bring ports up about the same time in your port channel. So all that's resolved, and now you can use any switch which conforms to those requirements, which is pretty nice. Now, some features are unfortunately still unsupported with clustering. This is my slide of shame. Right? I always like to say, well, the number of features on this list keeps shrinking. Unfortunately, in the last couple of years, we shipped some features like integrated routing and bridging and VTI, and we just couldn't make them supported with clustering at FC when we first shipped them. So we are working on adding that support, but again, I want to lay it out for you very clearly. Remote access VPN is not supported with clustering completely. Site-to-site VPN with FTD, there was a bit of a glitch. My engineering team accidentally disabled it, and I made them go back and enable it as of 6.2.3.3. So that's back in site-to-site VPN with clustering. Some of the DHCP features specifically related to VPN, so that's proxy, application inspection, probably not anything you use very often. And again, probably the biggest one right now for me is the new Firepower multi-instance capability, which we just shipped. So that's coming later this year. The reason why it's delayed is we really want to make it nice. So we want to kind of move clustering away from the hardware and move it more to the application. So you'll be able to do differently sized clusters and all that across a pool of hardware. So again, even though it's taking a little bit longer, it will be quite nice, I promise you. Very often I get questions about, well, how does clustering scale? Okay, so I got those 16 modules. How does my throughput connections per second scale? How do I size for my particular installation? So even though typically clustering does not give you any penalty in terms of throughput aggregation, if everything is symmetric. And by that, what do I mean by that? It means that the forward and the reverse leg of every connection lands always on the same unit by virtue of load balancing. So if you do something like a port channel, a firewall on a stick, with a single port channel and 2 VLANs inside-outside, typically all the flows without NAT will be symmetric. We'll talk a lot more about that. So in that case, it's close to 100%. Obviously, not every network is perfect, so I typically budget for about 70 to 80% of aggregated throughput. So you take the overall throughput of your whatever number of appliances you have on the cluster, it takes 70 to 80%, and that's a good estimate, conservative estimate. Now, on the connections and connections per second, connections that we do replicate, and we don't replicate all of them by default, connections that we do replicate, they scale at about 60% of the overall capacity, and connections per second scale at 50%. So even though it's not 100% linear scale, it is still scalable, even though you are adding more modules. So we don't copy the entire connection table to everywhere. And I said that not all connections are replicated by default. Well, there is this command that you can use, and the command's available in both ASA through the command line, FTD through FlexConfig, and you could actually specify if certain connections should not be replicated until certain uptime. So for instance, HTTP connections by default don't get replicated until they hit a 5-second mark. So you can say, well, I don't really care to replicate HTTP connections until they hit a 10-second mark. Why? Well, HTTP is very transactional, and it's very, very easy to recover. So if your users are going outside and something drops in the cluster, it typically makes very little sense to replicate those connections, make them survive, because the browser internally tries and nothing is even exposed to the user. If you are running some HTTP applications in data center, it could be a different story. You may want to disable this and say, look, those have to survive. So that's why we give you this command to change this behavior. On top of the unsupported features, some features, we call them centralized. And it means that they do not scale with clustering. So only one unit in the cluster will process any traffic pertaining to these features. And it's not a very long list. So stuff like control and management makes sense to centralize. There is a concept of non-per-session XLates translations in NAT. We'll talk about what that is a little bit later. Some inspection engines, site-to-site VPN up until ASA 991, where we did a distributed site-to-site VPN, specifically on Firepower 9300. So those kind of more of a corner set of features. And again, we try to, if we find something on the list that makes sense to scale, like SIP, for instance, we scaled SIP inspection quite a few years back because it just made sense to scale with clustering. We occasionally go back through the list and make sure we scale whatever makes sense on that list. So one big caveat for all those features is they do not survive a cluster member failure. So you have the cluster master, which is what handles all those connections, one unit in the cluster. If that unit fails, reboots, crashes, whatever, those connections have to be reestablished. They do not survive that kind of failure. So that's a very, very high-level view of clustering. And let's now dive a little bit deeper into the terminology. What is called what and who does what in an ASA or FTD cluster. So one concept that's a global concept across the cluster is the concept of a cluster master. So that's one unit which gets elected to do control and management plane tasks. So yes, question please. Yes? So the question is yes, if the connection is centralized and it goes to the cluster master, which is what handles centralized connections, those will have to be reestablished. Now, that's not to say that every single connection that goes to the master is reestablished, but only the centralized ones. Mm-hmm. 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 So the question is around the cluster master command. So there is a command to actually transfer master role. So typically it's elected, and you can actually issue a command saying, I want this unit to be the new master. I actually don't recommend using the command. In fact, if you use that command, it will cause more disruption. Because when you reboot the master, the cluster already knows who the successor is, because it knows all the priorities. So it can pre-plan, it can direct certain connections to the new master right away. If you do so manually by issuing the command, you kind of break that logic. So in fact, the cluster says, you know what, I could not have predicted who the master is going to be, so I can't try to transfer those sessions more seamlessly. So actually, if you want to transfer the master role somewhere, you would reboot or disable the cluster master unit to transfer the role automatically. In fact, that's why during upgrades, you would always upgrade each unit first, and then the last unit is the current master. It reboots, and this way it's much more seamless. So master is what you basically get into when you type in the management IP of the cluster, or the main IP of the data interface. Now, it does everything everybody else in the cluster do. Every unit in the cluster will process data, will process traffic, so there is no difference from this standpoint. It's not special in terms of not all traffic goes to it. It's not like a load balancer. It's just something we choose for management and control plane tasks. So when the unit first boots up, how does it join the cluster? So boot up, it starts looking on the special cluster control link. It's a special interface that cluster members use to talk to each other. And it's looking for the existing cluster. There are keep alive, hello, something to indicate the cluster is already there. So it waits for 45 seconds before doing anything. Any guesses why 45? Spanning tree, right? In case you hooked up to the switch and the port's not enabled, that's your forwarding delay, and that's where you can reliably say, you know what, by 45 seconds, I know there is nobody else on that link. So we should have heard from somebody, right? So in that case, if that's the case, the unit boots up, doesn't hear it from anybody, it becomes the master. Now, if the master is already there, it replies and the unit starts joining. Only one unit can join at a time by default. So if somebody else is already joining, this unit will stand down and periodically ask the master, hey, is it my turn to go ahead and rejoin? And eventually, it will say yes, and the unit will synchronize the configuration, the connection states, and then transition to an active state. And if anything happens at any point in that cycle, it will transition itself to a disabled state, and you can actually use those two outputs, show cluster history and show cluster info to figure out A, who is in the cluster, and B, if somebody tried to join the cluster and failed, why exactly that happened. In a recent code, we also made some optimizations to this join process, because there are two problems, right? One, we want multiple blades in a single, or multiple modules in a single 9300 chassis to join together. They're independent. They talk to the same supervisor in the chassis, so it makes sense. And two, if you have a certain number of interfaces hooked up to your 9300, you plan on using all three modules. If only one module joins, and the interfaces are brought up, that module is going to get a lot of traffic. Basically, whatever was designed for three modules, that one module, the first to join, is going to get. So there is this new command which tells the chassis to delay data interface bring up for this particular interval until a certain number of modules join. So you could say, I want all three modules to join before my entire big chassis brings up its data interfaces. And there's also a timeout. You can say, OK, after 5 minutes, I don't care to wait anymore. If something is happening, then somebody in the chassis can't come up. I'm not going to delay everybody else. I'm just going to go ahead and bring them up. In ASA 912 and FTD 6.4, that's coming up in April, we will also optimize the configuration replication process. Today, every time a unit joins the cluster, the entire configuration is replicated, even if the unit already booted up with a startup config which matches the current one of the cluster. So in the new code, we will skip the data plane configuration replication if we see that the checksum of the current config matches the checksum of what we are about to replicate. So that's a nice optimization. Now, there are some per connection roles. So the master is the global role, right? The entire cluster gets that one unit that does that. But for each connection, we differentiate several per connection roles. So every unit in the cluster is going to be in one of those roles I'm about to talk about. So, and the most important one is the flow owner. Flow owner is the unit which will handle every single packet for a connection for symmetry purposes. So once the connection is established, one unit in the cluster is going to be designated the owner, and from that point forward, until the owner goes away, nobody else will handle packets for this connection. That's just the way we pin processing of every single packet for a connection to one member. There are some cases where ownership may be transferred while the connection is up. Specifically in inter-site clustering, we have a feature which shifts connections between different data center sites, but it's an exception. So owner is selected based on who receives the first packet for a connection, which creates a problem. Well, how does everybody else know who the owner of any particular connection is? We use stateless load balancing, so theoretically, packets for this connection may land somewhere else. What happens? What happens if the owner fails? How do we recover this connection? So we introduced this concept of flow director. Flow director is a backup record of a connection. And the flow director, unlike the flow owner, is selected deliberately and consistently. So what we do is we take the source IP, source port, destination IP, destination port of every single possible connection. All the IP space, v4 and v6. And we divide that into 1,024 hash buckets. So we hash it, we create a hash, and the hash function produces one of 1,024 outcomes. And we divide that hash bucket space evenly across all cluster members. So each cluster member owns an equal share of that hash ring. So each cluster member, in theory, could be a director for some connections. And all cluster members compute the same function with the same input, so they can always take the source IP, source port, destination IP, destination port of any connection, any packet they get, compute the hash, and figure out who the director is. And that is used for two purposes. One, they can ask the director who the owner is. And two, they can recover the connection from backup if the owner fails. And we'll go through some flow diagrams showing how that process happens. Now, in that case, if somebody receives a packet for a connection it doesn't own, it has to figure out what to do with it. So the only packet that we know initiates the connection is TCP SYN, right? If the SYN is set and there's no ACK, it means it's the first packet for a connection, so we know it's the first one. If it's something in between or it's UDP, we don't yet know if the connection exists. So the unit getting that packet first checks if it is the owner, and if it's not, it has to figure out what to do with it. So it asks the director. It says, okay, well, for this flow, I compute the hash, I figure out who the director is, I got this packet, what do I do with it? The 3 possible responses. 1, the connection doesn't exist. If it's TCP and it's non-SYN, drop the packet. If it's UDP, check the policy, become the owner. The second response is the connection exists, but the owner doesn't. Something happened, went away. So the outcome is this unit will become the owner and continue processing this connection. Third outcome, and probably most common, the connection exists, the owner exists, here's the owner identity, so this unit will become the forwarder. So it will forward every packet it receives for this connection to the owner, so the owner can complete stateful processing. So that's the theory behind it, right? So now it's nice to put some flow diagrams behind all those concepts, so let's look at how a new TCP connection in the cluster is processed. So here I have a 3-member cluster. There's no any particular reason why I would pick 3. It's just nicer for the diagram. It helps me illustrate the point, but that's a 3-member cluster. Whether ASA or FTD, same thing. I have a client on the inside, I have the server on the outside, and a client wants to open a TCP connection to the server. Pretty common situation. So the client sends a TCP SYN packet toward the server, and we do use stateless load balancing. It's a port channel. Jumping ahead a little bit, it's a port channel, so the port channel will hash that packet to one of the 3 cluster members, all right? So it just so happens to hit the first one. Since it is TCP SYN, this cluster member knows it's the first packet for the connection, so it will check the policy, hopefully permit it, and become the owner. Simple. And then it will send that packet to the server. It does one more thing, one more little trick. So by default in ASA and FTD, we randomize the initial sequence number for every TCP session. Just a basic security measure. It doesn't cost us much in terms of processing, but helps to protect hosts with weak TCP stacks. So as long as we randomize that number, we might as well make it a little bit, do it in a little bit of a clever way, right? So instead of doing it purely randomly, we will actually encode the identity of the owner into that initial sequence number. So it makes no difference to the server. The server just gets the number. It's a number, right? Who cares? But it means something to the cluster. So what does it give us? So when the server replies, and again, by nature of stateless load balancing, it just so happens to hit a completely different member, right? This member can look at the acknowledgement number in a TCP session, TCP packet, subtract 1, figure out the initial sequence number, and decode the identity of the owner. And this way, it doesn't have to ask anybody. It doesn't have to ask the director. It can just go ahead and forward it back to the owner directly across the cluster control link. So that's an optimization for TCP, right? We don't have to ask director during session establishment. We know who the owner is from that TCP SYN cookie. If you disable TCP sequence number randomization, this breaks, and there is a different process. We'll talk about that when we talk about UDP. So do keep TCP sequence number randomization enabled for best performance. Then the owner is going to check the state, update the state, and send the SYN back to the client. One more thing left to do. The owner is going to update the flow directory. So it computes the hash for the connection, figures out who the director is, and sends an update saying, hey, we just created this connection. I'm the owner if anybody else asks. Simple, right? TCP is a simple case. Any questions? Straightforward so far? Cool. So UDP is a little bit more complicated. There is no flag. There is no way to figure out if the packet is first in the connection. There is no way to encode anything in the payload to hint who the owner is. So the same situation. Client sends a UDP packet. It hits a particular cluster member, but that cluster member doesn't know if this is the first packet in the connection or not. So what it has to do, it has to take that packet hash, compute it, so take the packet header, compute the hash, figure out who the detector is, and ask the detector, does this connection exist? And if so, who is the owner? So in this case, first packet for the connection, we know that, they don't. The detector says, nope, flow not found, so implies new flow. So this unit will become the owner, send the packet to the server, check the policy, permit it, send it to the server, and then it will update detector saying, hey, I just created this connection, I'm the owner. If anybody else asks, the connection exists. Okay, same situation. The server replies, hits a completely different cluster member. So again, same process, right? We have no idea, it's UDP. Maybe it's a new connection, maybe it's an existing one. So again, this unit will ask the detector, compute the hash, source IP, destination IP, source port, destination port, figure out who the detector is, the same unit, and the detector will say, yes, the flow exists, and the first unit is the owner. So this unit will redirect the packet back to the owner through the cluster control link. And then a loop is closed. Right. So that's TCP and UDP. And if you do disable TCP sequence number randomization, it becomes just like UDP, a little bit suboptimal. So what happens when the owner fails? So say the connection's established, and this unit is the owner, and the owner goes away, crashes, gets rebooted, gets disabled, something. All right? So the next packet for this connection hits the load balancing mechanism, port channel, and now it goes to a completely different cluster member. So now, whether it's TCP or UDP, this unit doesn't know, well, for TCP probably knows it's not the first one because the flags are already set. For UDP, well, it's a gamble, right? So again, it will take the source and destination IP, source destination port, compute the hash, figure out who the detector is, and ask the detector, hey, does this flow exist? And if so, who is the owner? And the detector will say, nope, the flow, well, yes, the flow exists, and nope, the owner went away. And by the way, since you got the packet for this flow, no good deed goes unpunished. You are now the owner, and here's the last known backup state of the flow. So this unit actually knows where we left off, approximately. And it can recover, become the owner, send the detector update saying, yes, I acknowledge I took ownership of this flow, and now the detector will always point to this unit as the owner. A good question that I once was asked, well, what happens if this flow doesn't send packets very often? What if we sit for hours and the owner failed, and for several hours, and this flow does not generate any packets? How do we assign ownership? Because by the time the next packet is sent, all the timeouts in the detector record have expired, and the flow will probably be purged without any updates. So that's a special case. If we don't see a packet for a flow with no owner for 15 seconds, the detector gets promoted to the owner. It's suboptimal, but it's necessary to maintain flow ownership of every connection. We can't wait forever for the flow to generate packets. So if we see a packet, we want to optimize to pick the best owner in the traffic path, but if that doesn't generate packets, too bad. We will just select detector as the owner. All good? Okay. So application inspection. That I'm referring to ASA style application inspection, not the layer 7 inspection stuff that FTD does. To be fair, ASA and FTD both run those inspection engines, but they run it in the data plane. So there are 3 different kinds of application inspection for ASA and FTD in terms of clustering. Some application inspection engines are centralized. So like we said, those connections will always go to the master for processing, and they do not survive a master failure in most cases. Some application inspection engines, like FTP for instance, are fully distributed, which means that every unit could independently process control and data connections. So FTP control session lands on one unit, FTP data connection may land on a different unit in the same cluster, and they will work that way. There is a third kind, which is kind of in between. Protocols like SIP, for instance, anything voice over IP, typically have one signaling connection, call control, and a whole bunch of media connections, one per channel. One for voice, one for video, typically. One for control, again, or TCP. So the thing about that is you really want to keep all of them together on the same unit because there are some timeouts which are very closely related. So those inspection engines we call semi-distributed. So the signaling connection, the control connection, can be sent to any unit in the cluster, and they are all independent. But every associated media connection is tied to the same unit that is processing the control connection. So that unit will own every single media connection which corresponds to this voice or video call. And that's why we call them semi-distributed. So we still scale if you have a lot of calls going through, but if a single call has a lot of media connections, like a big fat SIP trunk between two call managers, right? Two corporate call managers, where you have maybe 2,000 calls going across a single control connections, all those will go on a single unit because we have to keep them together. Network address translation, I always joke, I say it's the enemy of clustering performance. Why? Well, for a couple of reasons. But first, let's look at how they are processed. So the best one and the easiest one on the cluster is static NAT. Static NAT is done based on configuration, and the configuration is the same on all cluster members, so all of them will do static NAT independently. No need to talk to each other about it. One-to-one dynamic NAT, which is very, very infrequently used, by the way, is done initially through the master. So when a new connection comes in and it hits a one-to-one NAT policy, this unit, the owner, is going to ask the master to allocate a translation for this IP. But the master allocates it and sends it to all the units in parallel, so subsequent sessions from the same IP will be distributed. No need to ask the master. The worst case is dynamic path, so port address translation. That's the typical internet edge use case. You port translate something going to the outside. And in that case, there are a couple of caveats. So first of all, I mentioned per session XLates. There's a hidden slides, and by the way, I want to mention it now. There's quite a few hidden slides in the deck, right? Obviously, over the years, I constantly update the deck, add new stuff, but some of the old stuff is still very relevant. So I put it as hidden slides. You'll see like a little reference slide thing in the upper right corner. So there is a hidden slide talking about per session XLates and what those are, right? Per session XLates is when we create a NAT translation just for this one single connection. So back in the day on ASA, when you create a port translation, it will survive for long beyond when the actual connection is gone. So even though it's typically transactional like HTTP, we will create a translation, we'll keep it for like 60 seconds beyond the original connection. Connection's gone, but translation we're still holding on to. And that wastes resources. So per session XLates mean that once the connection is gone, we break down a translation as well. And that's the default behavior ever since ASA 9.0 code, unless you upgrade it, in which case it's disabled. And that's better for performance. Why would you not have per session XLates? Well, voice over IP, like SIP inspection protocols, they do port reuse. So it's advantageous sometimes because you want to come from the same IP and port, but that's beyond the point. By default, you should have per session XLates enabled, and per session XLates is what distributed in clustering. So if you disabled per session XLates, or you upgraded from before 9.0, you never bothered to change the config, those will always go to the master and cause low performance. ICMP, for instance, ICMP does not use per session XLates ever. It's a very low overhead protocol, so all ICMP connections through the cluster will always go to the master. But if you have per session XLates, again, the default, where each translation is tied to the session, that distributes, that scales in a cluster. All units do that in parallel. How do they do that? When you configure the path IP address pool for your interface, so your outside interface, you add certain IPs to the pool. You want to make sure that you have as many IP addresses in that pool as you have cluster members. Because the cluster members are going to distribute this pool among themselves, and each is going to get an approximately equal portion. So if you have 4 IP address, 4 cluster members, nicely each one gets its own path IP address on the outside interface. However, if you have 4 units and only 3 path IP addresses, 1 unit is starved. It cannot create translations. It will send all traffic back to the master. That's not good. So always make sure, if you do configure paths with clustering, always make sure you have enough IP addresses in the pool to share across all of the units. Extremely important. I had seen a lot of performance issues based on that. So that's the kind of the basic of the packet flow. Any questions so far before we jump into the data plane, control plane? Very nice. So the most important interface in the cluster is the cluster control link. I already mentioned it a couple of times, so that is something that the cluster members use to talk to each other. Send configuration, generate keep alives, redirect traffic. If the forwarder needs to redirect something to the owner, it will do it over the cluster control link. If a unit wants to ask the directory something, it will do it over the cluster control link. This interface must be completely separate from your data plane. Separate physical interface, no VLAN tagging, a separate subnet. Don't try to push both data and control plane traffic. Don't put 2 clusters, cluster control links on the same VLAN. There should be no crosstalk. That cluster control link should be completely isolated. If a cluster member loses connectivity to the cluster control link, clustering is disabled. For that very reason, you cannot connect 2 chassis, 2 appliances in the cluster back to back. What happens if you do that? Well, if you do it back to back, one appliance goes down, the link goes down on the cluster control link. It goes down at both ends. So both chassis lose the cluster control link, and the second chassis that is still fine, up and operational, will disable clustering because it lost the cluster control link connection. So it has to be a switched connection. You have to connect cluster members through a switch for the cluster control link. For best practice, I always recommend using VPC or VSS to have 2 physical switches in a logical bundle. I often get a question, well, is it a requirement? Does the cluster absolutely require VPC or VSS? No, you can connect them to a single switch, that's fine. It's just the best practice. This way, you don't have a single point of failure. You are investing in clustering, you're making sure there is no single point of failure in the firewall. You don't want a single point of failure in a switch. A cluster control link typically is a port channel, but it's a per unit port channel. Each cluster member will have a separate port channel to the switch to connect them for the cluster control. In terms of sizing, we recommend that the bandwidth of the cluster control link for each unit matches the forwarding capacity of the data plane. So if you hooked up each cluster member with dual 40 gig interfaces, theoretically, you should hook up 2 40 gig interfaces per cluster member for the cluster control link. However, you may not be passing 40 gig or 80 gig in this case through each cluster member. You may say, look, I am hooking it up through 2 40 gig links, each cluster member, but I only plan on passing maybe 20 gig of traffic per unit, maybe 10 gig. So it's okay to put 2 10 gig ports for the cluster link per cluster member. Again, it should match your data plane capacity, not data plane interfaces. So this way you can mismatch them and still be fine. One hugely, hugely important thing, like just one thing I want you to take away from this is that when you configure the cluster control link, you have to set the maximum transmission unit, L3 MTU, to 100 bytes above your largest data interface MTU. By default, on ASA and FTD, every interface has the MTU of 1500 bytes. So the cluster control link must be at least 1600 bytes to avoid problems. Why? When we redirect packets, we attach a little trailer to the frame to tell the receiving unit what this is, like how we got it, what context we have about it. And it's about 100 bytes, 67 bytes to be exact, but we say it's about 100 bytes. So if you have a 1500 byte packet being redirected, and now you attach a 100 byte trailer to it, you easily exceed your MTU of 1500 bytes. And that frame is going to get dropped, and you're going to have weird performance issues. You're going to have weird issues where the cluster stays together, but traffic is being dropped, you don't know why. So definitely always make sure your MTU on the cluster controlling is 100 bytes higher than the data plane interface. The two data interface modes. Well, there used to be two on the 5585, 5500X. There is only one on the new firepower appliances. So that one is the one I want you to use. It's called the spanned Ether channel. And what it means is this switch is going to build one big port channel across all cluster members. Just like VPC on steroids, right? VPC, it's only two switches. And here you have up to 16 appliances, but one single big port channel. And it's easy and it's nice because it's automatically bundled. There is one IP, one MAC address for all cluster members. Load balancing is done by the port channel on the switch. It's just very, very easy. The old way of doing that was the individual interface mode, where every unit had its own IP and MAC address on every data interface. And you'd have to configure something like Nexus ITD or policy-based routing or dynamic routing to fan your traffic across the cluster. And that's a lot more challenging than just having single IP, single MAC, and a port channel. So spanned Ether channel mode, like I said, one big port channel across all the units, one IP, one MAC. You must use port channels for everything. So you cannot have a port channel on the inside and two standalone interfaces on the outside. That doesn't work. Spanned Ether channel mode supports all kinds of interface types, both next-gen firewall and next-gen IPS. Individual mode, for instance, would not be able to support NGFW interfaces if we supported that on the new appliances. A good best practice is to do a firewall cluster on a stick to maintain symmetry in a port channel. Because like I said, asymmetry is the enemy of clustering performance. Like in NAT, right, if you have the IPs and ports changing the header, that typically means that the load balancing decision between the forward and the reverse leg isn't going to be the same, and you're going to have that situation where the forward leg of a connection hits one unit and the response goes to a different one. That's bad for performance because you have to redirect. So if you do Ether channel or firewall on a stick, then the load balancing decisions are the same. The same switch, whether it's the forward leg or reverse leg, without NAT, of course, they will both land on the same physical link. And it's just so much easier to pull units out of the cluster, add them. All it takes is the LACP negotiation, and the interfaces are bundled into the port channel, and there is no disruption to your network traffic flow. So clustering LACP is something we use for forming port channels. And again, a big misconception is, oh, this is something special, this is proprietary, this is not standard-based. Not really, it's just something we called it from our side. From the switch's perspective, it is completely stock, standard-based LACP. No special headers, no special extensions, completely by the IEEE standard. A cluster in spanned Ether channel mode supports up to 16 ports per unit in a port channel and 32 ports per cluster. So in a cluster of 16 members, you can bundle up to 2 ports per unit to a total of 32 ports in an Ether channel. Nice and even. On the ASA appliances, 5500X and 5585, we always recommend to disable 2 features on a Nexus switch. Graceful convergence, because it's only for NXOS devices, and adaptive hash, because it messes up with how the hash buckets are allocated, and it disrupts traffic when you have members going in and out of the cluster. In the new firepower appliances, we actually have portions of ASA code, on NXOS code embedded into the platform, so you no longer have to disable LACP graceful convergence. In fact, you should keep it enabled. It will bundle the port channel faster. You should still disable adaptive hash. Now, one thing I want you to also do, when you configure a spanned Ether channel on a cluster, and you pretty much have to if you use clustering on the new appliances, always set up the virtual MAC address. Why? Well, because by default, if you don't do that,
the port channel inherits the MAC address of the cluster master. Well, if the master goes away, it gets reelected, that MAC address changes, and it changes the MAC address on your port channel. And that causes a disruption, because your MAC address of the cluster keeps changing. That's a bad thing. So always configure a virtual MAC address for your spanned port channel to preserve those, to avoid those disruptions. A cluster supports all kinds of dynamic routing, just pretty much the same as what ASA or FTD support. So that's all the way from RIP down to BGP and PIM. In a cluster, all the routing control plane logic is done on the master. So the master will create the adjacencies with neighboring routers, and then it's going to replicate the routing table to all the other units. So this way, you would only have a disruption in your routing process if the master fails. If any other unit fails, no big deal. Nobody even cares, because there is no disruption to the routing process. In individual mode, which we're not going to talk about too much because it's something that's no longer supported, in individual mode, every cluster member runs its own dynamic routing process. So every cluster member going in and out creates a disruption in traffic forwarding because routing has to converge. Now, even though it's nice, right, and the master in clustering does the adjacency and replicates the routing table elsewhere, it creates a bit of a challenge because the adjacent router doesn't know that, right? To an adjacent router, it's just a device. It has no idea it has any kind of redundancy. So when a cluster member goes, or cluster master goes down, gets reelected, all that the neighboring router sees is that, well, my peer went down. So even though the cluster is perfectly capable of forwarding traffic based on the existing routing table until the new master reestablishes the adjacencies, the peering router drops the route saying, well, this router, my peer router went down. I'm going to reestablish from scratch, and while I'm reestablishing, I'm not going to route any traffic toward it. That's bad, because that kind of defeats the purpose of having a routing table replicated inside the cluster. So there is a feature called nonstop forwarding and graceful restart, which helps avoid that problem. So what does it do? When the OSPF or BGP adjacency is established, the neighboring router and the cluster, they indicate to each other that NSF or GR is supported. So when the master fails and the OSPF adjacency goes down, the neighboring router knows that this particular cluster has redundancy built in. So it's not going to purge the routes. So it's going to negotiate the new OSPF adjacency with a new master, but it's going to keep forwarding based on the last known routing table. And the same thing works in reverse. If the primary routing processor in the router goes down, the cluster is not going to purge any routes toward the router. It's going to keep forwarding based on the last known routing table state. So that's nice. You get this bidirectional interaction where even if the routing adjacency is reestablished, the traffic is still flowing. It's a very good idea to check the traffic distribution in your cluster to make sure that everything is flowing correctly. So there are a couple of commands you definitely want to look at. Again, the same on both ASA and FTD. And one thing you want to look out for is that each cluster member is getting approximately same number of connections. All right, so if you have a situation where one cluster member is processing thousands of new connections and others sit a little bit idle compared to that, it means you want to tweak your Ether channel hashing algorithm to maybe include the source and destination ports, make it a little bit more granular. Right? The other one you want to watch out for is the amount of traffic being processed locally versus being forwarded. If you have a high amount of forwarded connections, it means that your traffic is very asymmetric. Maybe you are using NAT. And when using NAT, there is absolutely no way to avoid that. You're going to have asymmetry. It's something you have to live with. But if you aren't using NAT and you're seeing very low locally processed percentage levels, it means something else is wrong. Maybe you have way too many centralized connections. Maybe you inadvertently enabled a feature which does that, but that should not be significantly below 100% if you don't use NAT. Yes, please.
Forwarded packets, does that mean that you forwarded over
Yes, the question is, what does the forwarded packets means? Yes, it means that those packets are being redirected through the cluster control link. So it means that this unit is not the owner of those packets, cannot process them locally. Mm-hmm. Mm-hmm.
And between ASA or FTD
Mm-hmm.
to have absolutely the same load balancing configured.
Mm-hmm.
So all nexuses, not all FTDs, and the data is the same.
So the question is, do you need to align the load balancing algorithm on the cluster itself and the adjacent switches? And the answer is no. The only thing that matters is how the traffic is delivered to the cluster, because the cluster is stateful. The switch isn't stateful, so it doesn't care. So you don't need to align those. And it's actually hard because different devices use different formulas for calculating hash, so it's usually not even possible. Typically, in FTD, you have to have an out-of-band dedicated management interface. In ASA, it's optional for the cluster. I always recommend having it because this way you can connect to each cluster member independently troubleshooting. Also, things like SNMP, for instance, they aren't centralized. In other words, if you poll one cluster member, you're only going to get data over SNMP for that very cluster member. So if you want to get data across the entire cluster, you need to poll each individual unit separately. So you have to have a per unit management IP address, which is possible in spanned ether channel mode as well. Yes.
Regarding this management, why it's not possible manually to set up IP address, management IP address for the cluster members? You know, there is only one option to specify the pool, and then it depends, you know. The first one will get the first IP address. Why it's not possible to manually, you know, I don't know, this cluster will have this IP address, and I don't know, this one.
That's a good question. So the question is, well, how do you, so the way you configure the management IP addresses in the cluster, you give a pool, a set of IP addresses, and the first member that joins grabs the first one, the second one grabs the second one, so it's a little bit non-deterministic. So a question is, well, why can't we assign those manually? And the original reason was that it was a little bit easier. It was very complex to represent it in the CLI. But what happens is, and how you can actually make that consistent is, even though it's based on the order of join, it is sticky. So if you bring them up like unit 1 comes in first, unit 2 comes in first, you actually have control over how they join. And once they join, the IP assignment is tied to the cluster unit ID, which does not change. So even if the unit drops out and comes back, it will get the same IP address. Yes, correct, exactly. If you do rename them, then the assignment changes. And we actually had the enhancement on the list for quite some time, just we haven't gotten to it yet. But yeah, I get the requirement to be able to do it statically. We are tracking this enhancement. It is just not there yet. But like I said, it is consistent. So yeah, unless you rename it, it will be consistent. If you do rename it, then it does absolutely change. That's a good call out. There is a cluster exec command which allows you to get into one unit but execute the command across all of them in parallel, which on ASA is super handy for upgrades, for instance, or getting something like show tech, right? Because you can execute the command on all the cluster members in parallel, and the response comes back nicely to a single console. So definitely use that if you need to troubleshoot. By default, we, like I said, monitor the state of the cluster control link, and if it goes down, clustering gets disabled. The cluster control link is used to generate keep alives between all the units and the master. And there are some settings you could tweak in that sense. Depending on what kind of response we get to the keep alives, the master may kick the unit out of the cluster. So for instance, keep alives by default are generated every second, and you miss 3 of them, the unit is out of the cluster. The units also compare the state of their data interfaces. It's not a strict, oh, is it up, is it down? It's how many do I have up versus the master. And so if some unit has more interfaces up than the master considers itself failed. If some unit has fewer interfaces up than the master, that unit is considered failed. So the whole time indicates what is the maximum amount of time the cluster master will wait for a keep alive from a unit, and we generate 3 keep alives for this interval. So if you configure it as 1 second, we generate a keep alive every 333.3 in period milliseconds. If you configure it to be 3 seconds, we generate a keep alive every 1 second. So in this case, 1 second is the maximum time a unit cannot respond before getting kicked out of the cluster. Sometimes it makes sense to disable health monitoring in certain interfaces, like management interfaces. You don't want your cluster to fall apart just because your management interface briefly went down. So a lot of customers of mine disable health monitoring on the management interface. Then there are cluster controlling and data interface monitoring and rejoin parameters. So you can actually tune, if the interface fails, the unit gets kicked out of the cluster, you can tune how long it waits before trying to rejoin and how many times it actually tries to rejoin after a failure. Because sometimes it's just a permanent failure and you'd rather stay down, not keep trying to come up, check, and come back down. So those commands control that for cluster controlling and data interfaces. There is a new one that's for the system. So prior to ASA 992 and FTD 623, if there was some kind of a weird internal system failure in a cluster, it would disable itself and not rejoin. So we added a command to attempt an auto rejoin in that case as well. Though, if you did experience some kind of a low-level system failure, you probably want to call TAC right away and figure out what's wrong. Because yes, it will keep trying to rejoin, but we already know the state of the system is not optimal. Something happened, it was unforeseen, you don't really want that situation. Unlike the interface-driven failures where interface may come up, you know, the switch rebooted, interfaces came down, came back up, that's fine. But a system failure is a lot more internal to the cluster versus something external. So now let's talk through an example of how you actually configure clustering on the Firepower 4100. So first of all, for the legacy ASA appliances, I'm not going to talk about how you configure clustering in those. There are actually a bunch of hidden slides in the deck showing you the process exactly. But I just want to step through the preparation process to make you appreciate just how much easier it is to do so on the new Firepower appliances. So on the classic ASA appliances, first of all, you had to connect to the physical serial console. So you could not do this whole thing remotely. You had to be on the console because we have to reboot a couple of times. You had to clear the configuration. You had to change the way we handle jumbo frames because the cluster controlling MTU has to be higher. So you had to enable jumbo frames, specifically reboot, change to multiple context mode, do a lot of manual things. So again, you were better off camping out at your data center right next to the cluster with a big cup of coffee and making sure everything goes well. If you do it over the network, and you could theoretically attempt that, there is a good chance you'll have to drive into the office anyway because something got rebooted and you didn't get access back over the network. So there's a lot of hassle back on the classic ASA appliances. So some of the cool things we did for the 419300 appliances for clustering, well, one call out is, like I said, only spanned Ether channel mode is supported. But the supervisor does a lot of initialization work for you. So you don't have to go on a command line and configure the IP address and management pools, all that. You do all of it in the UI, and a supervisor will push that configuration for you. There are elements like site ID, which are used for inter-site clustering, also configured in the UI. We also, for the 9300, to avoid an outage when you lose all 3 modules in a single chassis, we actually do the off-chassis backup in a different physical appliances. So all connections are backed up locally and also remotely for extra resiliency. We also generate syslogs to indicate a possible oversubscription. So those are not foolproof, right? They try to predict, based on your current traffic load, if one module in a cluster fails, or the entire chassis fails, will we potentially cross 100% utilization? So those syslogs are generated, and you keep saying that, right? When we developed the formula for those, I worked it out, and then we did it in the code, and now if you ask me how exactly the formula worked, I don't remember. It was, again, it wasn't foolproof, but we built in some hysteresis to make sure that it's not too high, not too low. So there is a little bit of logic to that, but again, my memory is not that good to remember things I did many years ago. So if you really, really need to know, I can probably go back and look it up, but again, take them as a recommendation, not an absolute guarantee. So when you do clustering in firepower appliances, it's a lot easier. You can do the whole thing over the network. In fact, you must do it over the network. You should not go through the console at all. There's no serial console connection required for it. So all you have to do, make sure the supervisor is reachable over the network, and you're good to go. Set up things like FMC, obviously. Set it up first so you have FMC up and running. If you are deploying FTD cluster, hook up cluster smart license or FXOS firepower smart licensing, get the right images on the chassis, clear the existing logical devices on your chassis as well. If you already have a standalone logical device on the firepower chassis, you cannot do clustering, so you have to clear that out first. Get a nice little diagram to figure out how things are going to get connected, much like this one, right? This is my cluster. So what I'm going to be doing here, I'm going to be setting up a 2-unit cluster of 4140s with FTD. And I'm going to have my separate VDC on a Nexus switch for data and my separate VDC for cluster control link and management. Yeah, it could be same Nexus switch, but 2 different VDCs. Doesn't have to be, but I just like to keep things a little bit separate between data plane and control plane. I am using VPC because, again, it's the best practice to avoid single point of failure. So first of all, I'm going to hook up my FXOS management interface. That is used to manage the chassis, not the FTD application. So that link needs to go to both FXOS chassis as well as the Cisco Smart Licensing backend for ASA, but it's a good practice to do for FTD as well, and my administrator console. It's all over the network. Then I want to designate an FTD management interface, dedicated management interface for FTD specifically, and this is going to be Ethernet 1/8 on both chassis, and that's going to go to my FMC and also my administrator station. Then I'm going to hook up my cluster control link. My cluster control link is a special port channel. It's called port channel 48. It's typically, you should keep it as port channel 48 unless you have a compelling reason to change it on the chassis. And that's going to be a 2-port local port channel for each chassis on a separate VLAN on the switch. So I'm going to hook that up like shown, right? Notice it's a separate port channel. For each cluster member, it's not stretched across both chassis. It's 1 per chassis. That's very, very important. I've seen a lot of people make the mistake of configuring those as a single port channel, and it just breaks it. And finally, my Ethernet 1 and 1/2 on both chassis are going to be my data port channel. I'm going to do a firewall on a stick. So I'm going to have 1 4-port port channel, span port channel. Notice it's spanned. Now the data plane is spanned across both chassis. It's 1 single big port channel. So the switch will see the entire cluster as 1 logical device. And so that's going to be my data plane. Make sense? Clear? All right. Yes? Mm-hmm.
Did you now say that it is the practice to put the data port and CCL link across 2 Nexus switches?
Thank you. That's an excellent call out. It is absolutely a best practice. Notice what you said, right? It makes complete sense if you have VPC to cross-connect. Like you don't want, for instance, in this diagram right here, if one of the switches, like the second switch goes down, it takes out the entire cluster member. So in the real life situation, which does not require you to create a PowerPoint slide like this, you would cross-connect them. So those links, the orange links and blue links, will cross-connect between the 2 different chassis, switch chassis, and the cluster. But again, because I had to create a nice looking diagram without too many intersecting lines, that's why I did it. But it's absolutely a great point to make, that you always want to cross-connect. It's typical rule number 1 of VPC. You want to cross-connect all those links. Correct, yes, all the links, right? So you always want to have, from each cluster member, you want 1 cluster control link interface going to each of the switch chassis in the VPC, and for the data interface, same thing. Each cluster member always connects to both. This way, again, if you lose a switch, you aren't going to lose the entire cluster member. The only exception is inter-site clustering. We'll talk about that later on, but then typically you'd have a VPC per site. Excellent. So first of all, you go ahead and create your interfaces. This is the Firepower Chassis Manager on the 4140. So you have your data port channels. That's my data port channel. And by the way, in the slides, I show you which you have to configure on all chassis versus just the master chassis. Right? So this is something you configure on all chassis. So this is my data port channel. So it's going to be the same on both Firepower 4140 appliances. This is my cluster control link. Like I said, this special port channel 48, it's already pre-created for you. So all you have to do, you have to add those 2 ports for the cluster control link. And this is my management interface for my FTD. Now, once you set it all up, one thing to keep in mind, the only port channel which needs to come up is the cluster control link. If your data port channel does not come up, stays suspended or failed, it's okay. That's expected, in fact. The cluster member is not going to bring up those data link interfaces until it is joined the cluster. And now we don't even have the logical device hooked up. So those data ports are going to stay down until you deploy the device and it actually joins the cluster. So that's fine. The only one, again, that has to be up at this stage is the cluster control link ports. If those are down, you've got to go back and troubleshoot why before you continue on. Then you go ahead and create a logical device. You click the button, add logical device, you name it something. It's a local name, so it doesn't matter. You select Firepower Threat Defense application. You select the version. For now, we only support native deployment types. So now we have native and container. For those of you who may have had an opportunity to attend my session yesterday, we have this new feature called Firepower Multi-Instance. So we support Docker-based container instances on a single module. So that's container type. That does not support clustering yet. That's coming by end of this year. So for now, we select native. Native means the application will take the entire module. And then I say, yes, I want to do cluster, and I want to create a new cluster versus joining an existing one. So now I get to this nice screen. I select whichever interfaces I want to assign to my cluster. So port channel 10 is my data plane. Port channel 48 is my control plane, my cluster control link. So don't unassign PO48 from the device. It wouldn't work if you do so. And then you click on that FTD icon on the right side to go ahead and configure the cluster-specific parameters. So things like chassis ID, that has to be unique within the chassis. So if you are deploying 4100 cluster, each chassis will have its own ID. If you deploy a 9300 chassis cluster, each chassis will have the same ID, but all the 3 modules on the chassis will share that one chassis ID. And we use that ID to create backups, connection backups within the cluster. Then there is the site ID. That is specifically used for inter-site clustering. If you have multiple sites, multiple data centers, you want to make sure you designate this correctly because, again, we use that for traffic localization. And we'll talk about that when we talk about inter-site clustering in a lot more depth. The cluster key is something we use to encrypt messages on the cluster control link. Only the control plane messages, not the redirected traffic. So that one has to match across all cluster members. If it doesn't, you will have weird issues with cluster members not wanting to join, not wanting to see each other on the cluster control link. The name, just a name, right? Nothing special to it. And then there is the management interface, which we pre-created. And you could also specify the cluster control link subnet. That's a new feature. It's actually a very interesting engineering task we went through. So by default, on 41 and 9300 appliances, we picked 127.2.0.0/16 as the cluster control link subnet. And our assumption was that a cluster control link is fully isolated. So there's no other traffic on it. It doesn't have any other endpoints on it. So we had to pick some subnet, which was pretty wide open. You wouldn't have too much crosstalk on it. It wouldn't interfere with anything on the network because 127/8 is reserved for loopback addresses. Now, what we found out is, well, some customers wanted to carry the cluster control link subnet between sites over OTV, or they hooked it up to ACI. And interestingly enough, both OTV and ACI internal architecture also picked the 127.0.0.0/8 subnet for the very same reason. They assumed nobody would use that on the network. And as a result, they did not exactly allow that subnet to be carried across their data plane. So we had situations where, well, first of all, the cluster control link would not work when hooked up to ACI, because again, they used the same subnet for something else. Or when you extend it across OTV, same deal. So that was a bit embarrassing, so we went back and fixed it, so now you can specify your own subnet. We still kept the 127.2.0.0 by default, but you can go ahead and you can specify a different subnet for your cluster control link. So that's just an interesting engineering process fact. On the second tab, you have things like FMC registration key. It has to match what you would eventually put into FMC, otherwise FMC would not connect to the cluster. The CLI password also. Yes, question please.
But if you have connected your cluster control to the ACI and it's working, then by that certain I think it's okay, or can be some side effects by that?
So the question is, if you already hooked up your CCL to ACI and it's working, do you have to change anything? No. It is typically, so it's still tied to multi-site, like multi-pod, multi-site deployment. So if it's working, that's fine. But again, there were cases where it didn't work, and that's obviously not fine, and you have to change that. Yeah, not to say, I apologize if I gave you the impression that every single ACI deployment is affected. It's just certain specific configurations. Much like, again, OTV is used to create an overlay transport. ACI has something very similar in certain configurations. So the CLI password to get into FTD itself. So you typically wouldn't do that unless you're troubleshooting. The Firepower Management Center IP address. What IP the cluster will connect to add to FMC. That's the real IP address. And what I mean by that is what is actually configured on FMC. Then you also have the default domain, you have the firewall mode, routed to transparent, you set up the DNS server, and now, like I said, you have to have the real IP of the FMC up above. If the FMC is behind NAT, you would put the mapped IP address here as well, so we could actually connect to the FMC. The host name and the eventing interface, unless you are using the management interface to generate events toward FMC, which most folks would do that. All right, so notice, just a call out, and notice that I'm specifying a lot of bootstrap parameters here. So you wouldn't have to do it on a CLI, you don't have to do it on every single chassis. So that's what makes it nice to deploy a cluster on the Firepower 4K and 9K to do that kind of stuff. And kind of deviate a little bit, we are working on a zero-touch provisioning feature in FXOS 2.6.1, which is shipping in April, and so you would be able to do all that without even having to go through the initial bootstrap dialog when you hook up the chassis. You'll basically pull the IP, management IP from DHCP, and you could connect back and use API to auto-provision the whole thing. So you could do the whole thing remotely with a script. Once the chassis plugs in, it sucks in the configuration, and you're good to go. So on the third tab, you set things like the management IP. That's the out-of-band management IP for the cluster. In this case, it's a single 4140, so it's one IP address. And if it was a 9300, for instance, you would have a pool of IP addresses, and that's the one where we assign it based on which module comes up first. And again, it's something that we definitely need to look into in terms of static assignments, static IP assignment down the line. It makes sense now with the new model anyway, so that's definitely something we have to address. But here again, 4140, it's very deterministic. Single IP, single management IP, single app, so that's fine. And now you click OK, save, and the device, the logical device, goes in this install state. You go grab a coffee, grab a donut, whatever, and then I don't know what happened there. It's kind of weird, but what it's supposed to show is that the logical device is now online. So now it is it's installed, and now it's ready to be added to the cluster. That's the first one. Now we might as well want to go back. Wow, that's kind of wild. What you click on this, there's a button called clone. in this view, there's a button called Clone the Configuration. So what it does, it clones the configuration of the master chassis, and you get this nice thing where you can go ahead and copy this into your buffer, and so you don't have to go through every single step that we did on the previous slide, right? You still have to enter the keys manually because the keys we don't put in the clear, it's insecure, but all the other stuff, all the interface config, it's all in this little blurb of text. So when you go on your second 4140 and you create the logical device, what you say is, you say, okay, I want to join the existing cluster. And you click this box, check this box saying copy config, and you paste that bundle of commands into that window, and now you don't have to, again, type in every single thing. Again, it's all pre-populated for you. The interfaces, the FQDN, the DNS IPs, again, the only things you have to type in is the per unit management IP address and all of the secret keys. And now you have 2 units in the cluster. Now, again, the slides have some hidden slides. The deck has some hidden slides, which talks about how you would add the cluster in FMC 6.2 and earlier. And it was a little bit complicated. So you had to first add the device, and it was totally counterintuitive, by the way, and I totally acknowledge that, right? First you would add the device, and then you would add the cluster. And it kind of made no sense, right? Because if you know you have a cluster, you want to add the cluster. So in FMC 6.3, you don't now have to add every single cluster member separately. You only have to add the master. So you have the master IP address, you say add device, all this add cluster nonsense is gone, right? So you click add device, and you put in the master management IP address, you name it something. You put in the FMC key, which should match what you provisioned on the FXOS side. When you did the chassis manager, you put the FMC registration key. That has to match what you provided there, otherwise they won't work. You select the default access policy, has to be pre-created. You select the licenses. So the licenses, the subscription licenses, have to be aligned for every cluster member. So if you have 16 cluster members, you have to have a license, a subscription license for every one of those 16 members. That's just something that happens. Now, if you don't have enough, it's not really going to do anything for you. It's going to nag you a lot, saying that you're out of compliance, but it's not going to stop any traffic. It's not actually going to do anything active to break your network, which is nice. And then if your managed device is behind a NAT device, you can also specify the mapped IP versus real IP in the screen. And then you click add, and eventually you get both cluster members added at the same time. So again, it's much nicer than in FMC 6.2 when you had to first add every single cluster member. Imagine doing that with 16 chassis, right? And then you have to actually add it as a cluster. So here you just add the master, and it sucks in every other cluster member into the cluster automatically. Yes?
When we had the cluster had the 2 remarks for the master and for slave, do I then determine that the cluster is up and running? Because in version 6.2, I've seen that, like, I have one part of the cluster not down, but I still have 2 green check marks.
Yeah, so the question is around the 6.2.3. There was some disparity between which cluster members were up or down. Yeah, there was some issues, so we addressed a lot of those in FMC 6.3 as well, like how we actually monitor the state of the cluster. That was part of this enhancement. So you think you're done, but there's one more thing to do. Remember, I told you you always have to set your cluster controlling MTU to 100 bytes above the largest data interface. So you go and edit your cluster properties, edit CCL interface, that's port channel 48, and you set the MTU, in this case, to 1600 bytes. And then you save and deploy, and you're good to go. You are ready to configure and deploy your cluster. There are plenty of troubleshooting commands and monitoring commands on the CLI to look at all kinds of cluster states. Some of them go pretty deep into the debug level outputs, so you don't have to break those out unless you're working with TAC. I always recommend looking at syslogs first. Syslogs are very, very detailed, especially if a cluster member keeps dropping out of the cluster, they will always tell you why. So when we designed the syslogs, I actually made sure we went back through the entire spec and we changed all the syslogs back a long time ago to make sure that they truly reflect what happened and how you can mitigate that. So definitely look at your syslogs first. So now we come to the probably most challenging, most interesting section of the entire talk, and it has to do with multi-site clustering. So the question is, by default, we try to, on data link interface failure, we rejoin 3 times. And if we failed on a 3rd time, we disable the unit permanently. So the best practice is, that's the best practice. To me, if you have such a major interface failure, which didn't get resolved on its own for 20 minutes, something really broke, all right? And you better go and figure out what's broken. You could change it to unlimited. So there is a way to make those joins unlimited. But to me, that's just causing an extra disruption. Because every time the cluster member comes up, tries to join, it does affect the cluster a little bit. The traffic should be flowing fine, but there is some control plane interaction. And if you know you're going to drop out anyway, why bother? Right? So to me, 3 failures to join in 20 minutes, consecutive failures to join in 20 minutes, that's kind of where you have to draw the line, come in and figure it out. So the question is, when you fix the problem, what do? Do you reboot the cluster or you just re-enable it? You can re-enable it. That's all it takes.
You tell that you get some code from Nexus switches and put this to eliminate the need of intelligent traffic directory balancing. It is in ASA and FTD both or only in FTD?
So the question is, yeah, around the, I think you're referring to LACP graceful conversion. So when we merge some NXOS code into Firepower platform code, we inherited a lot of NXOS optimizations like LACP graceful conversion. So first of all, it doesn't really interact with the Nexus ITD as a separate feature. It's like PBR with a nicer interface. But it applies to both ASA and FTD. So clustering, the port channel bundling is done at the Firepower FXOS level. So every application running on a chassis will take advantage of it. So it's either way. ASA appliances did not get that code. This is only FXOS.
Is the cluster health monitoring on the port channel or on the similar interfaces?
Cluster health monitoring, the question is it done based on a port channel or individual interfaces? It's based on a port channel. So whatever the logical interface unit is. All right, so let's kick it off. So by the end of this section, and I understand a lot of this goes into very, very deep detail on inter-DC technology. So this goes well beyond clustering. And that's just kind of one of my passions, right? When we first shipped clustering, and I keep telling a story, it's still funny, right? When my D manager back in the day, I asked him, well, what do we do? So clustering, that's great. So what do we do if a customer wants to deploy cluster across multiple buildings, multiple data centers, multiple geographies? They said, no, why would anybody do that? That doesn't make any sense, right? Well, and long story short, 6 months later, we get the first customer who is trying to do like an inter-campus deployment. Or then we have a customer who's trying to do it between a data center in Texas and a data center in California, right? And well, the customers, I know our customers are extremely creative. You guys always find a way and in a good way, right? To use the technology to solve a problem which perhaps we didn't think of solving it that way, right? So we went back and we're like, okay, well, we gotta support inter-site clustering. So that's been something I really put my mind and heart to, and I'm very proud to see where we've gone. And we've got a long way to go, but at least based on what we did, I think we did a pretty decent job with that feature. So back in ASA 9.1, we just did some very, very basic testing to be able to stretch a single cluster across multiple different buildings. So we tested for latency, cluster control latency so we supported up to 10 millisecond one way, and we ensure that the configuration replicates correctly. Then in ASA 921, we we did it with spanned Ether channel mode. We made some changes, so in transparent mode, you could actually do something we call a split spanned Ether channel across geographies. I'll show you what that is. So that was only transparent mode. In 9.5, we added routed mode. There was some additional work, a lot of work actually, to be done to make that supported. Then in FTD 6.2, we support inter-site clustering, unfortunately only with flex config, but in most cases you don't actually need flex config, and we'll talk about that. And then we partnered up with ACI folks in ACI 3.2 to design this Anycast services feature in ACI, which makes it all very, very nice and cool for multi-pod deployments. Makes it all very nice and cool how you can deploy the cluster across multiple pods and have a single IP, single MAC address, and not mess with any flex config, and ACI directs traffic automatically to the right cluster, and we'll talk about that, and it's all very cool. So first of all, typically the most common topology you would use with inter-site clustering is called a split spanned Ether channel cluster. It's a mouthful, and that's what happens when people let me name things. Right? I'm not good at naming things. I'm somewhat decent at designing things, but naming things is just not my strong suit. So split spanned cluster. And what it means is you have one cluster stretched across a geographic distance. And the cluster controlling, by the way, in all those diagrams, again, for the sake of simplicity, I used a single link for CCL and a single link for data. That's not the best practice. You would always cross-connect. But in this case, the cluster members at each site will only connect to the local switches. So there will be no cross-site link for cluster controlling. You would extend that cluster control link between sites for sure, because they need to be able to talk to each other. But again, all data and all cluster control link connections are site-specific. Right? And that's done on purpose to localize traffic to each particular site. From the cluster perspective, it's one big spanned port channel, but we do a little trick here. So from the Nexus, from the switch perspective, we configure two different port channels. It's pretty wild, right? So we kind of break the concept of port channel by doing one big port channel on a cluster, but two small port channels per site on the switches. And it works because the cluster does not force a peer switch in LACP to have the same system, the same peer actor ID. So there is a certain ID in LACP, and normally, if you bundle two switches, if you do it like this, the port channel wouldn't bundle because the cluster would think, oh, I'm peering to two different devices. That's a mistake. But it does allow this topology specifically for inter-site clustering, and that's what does the localization of traffic. So notice, when each site wants to send something into the cluster, it will only do it to the local cluster members. Why? It's more optimal, right? You don't want to use data center interconnect link because it's very expensive. You pay in your service provider for the bandwidth. And so the data VLANs typically aren't extended for north-south. Definitely not. For east-west, east-west is when the cluster is the first hop router, default gateway for your host on the extended subnet. Then you may extend that, but you have to have some filters built in to prevent a duplicate MAC and IP address. Again, we'll talk about all that in great detail. So the most common topology for inter-site clustering is north-south insertion. So that's when your cluster sits between your distribution layer and your core. So it's not controlling traffic inside the data center, it's controlling traffic in and out of the data center or a tenant. And yes, you extend the cluster across both sites, and then you use typically some dynamic routing protocol like EHRP or RSPF or BGP, whichever, to peer between your distribution and core routers at each site. And the cluster is typically transparent, so it doesn't mess with your routing too much. And then what you do, you also establish peerings between the routers, the north routers and south routers at each site, and you carry the same VLANs. Those are layer 3 links, not layer 2, layer 3. So then what happens is your best path outside, your default route, gets advertised from the core to distribution, and your inside networks get advertised from distribution to core, and the same routes are exchanged across those extra cross-site links. But the best path inbound and outbound is through the local site. So when the connection is established, it will follow the best path. You got inside one at subnet at DC1, inside two at DC2. Those aren't extended, right? Unique subnets per site, and so the traffic flows nicely like that. Now, if this cluster member fails at this site, no big deal, right? The routing will still have the path through the second cluster member, and it's all fine. Now, the interesting thing happens when both cluster members at this site fail. Then this route, the shortest route, is no longer there, so you will reroute across the intersite link between the routers. Now that route becomes preferred, and the cluster member at the second site picks up the traffic as if nothing happened and carries it forward. So no impact to your traffic, completely seamless to the application. Again, that's the most common intersite clustering setup. I have tons of customers doing that very, very successfully. The easiest to set up, no extra config needed on the cluster itself. So here's an example. Again, I'm not going to go through every single command, just to kind of give you an appreciation of what you would typically do. So this is my north-south cluster, transparent firewall in the middle. One thing I do in this example is it is based on PBR. How many of you heard about this VPC loop prevention problem with VPC dynamic routing on Nexus when you peer between a cross VPC device? Not many of you? Okay, well, a couple, right? So the problem is attributed to dynamic routing, but it's really a VPC loop prevention problem. So the problem goes like this. If a Nexus switch in VPC has a port channel that is a VPC port channel, it will not accept or send a frame which is destined to its peer chassis, which also has a port in the same port channel. So what happens is if you're doing dynamic routing peering, you have cross-connect, right? Cross-connect, you have a router here, cross-connected to both Nexus chassis and VPC. If this router wants to peer with the right chassis, or my right, your left chassis, but it so happens that the port channel forces it to load balance to the left chassis, the frame load balances this way, that frame will never reach the other chassis, because the VPC loop prevention logic says, hey, this router has a direct path to whatever it's trying to go. It's my peer. If it wants to reach it, it should just send it straight there. But it's dynamic routing, right? It's layer 3 over layer 2, so it goes like this, and it doesn't work. So there is a VPC peer gateway feature in Nexus OS, and again, that's nothing to do with clustering. I'm giving you a little bit of Nexus insight. A VPC peer gateway feature which solves that problem now in NXOS 7.2, I think, across most platforms. But anyway, for this reason, this example is built on PBR, which is kind of not pretty, but it works, even if you don't have VPC peer gateway. So here what you got going on, right, it's your typical switch configuration, firewall on a stick. Firewall's in transparent mode, so it's bridging VLAN 10 inside, VLAN 20 outside, and I have this very weird PBR. It basically says for each VPC pair at each site, if I can reach the outside from my local peer on the other side of the cluster, use that path. If not, reroute across sites. So I have this on all sides. Now, one big call out, like what do I want you to take away from this diagram? If you do it like that, notice that the MAC address A and MAC address B, those MAC addresses on the routers or switches are metered between sites. That's a strict requirement in this topology. Why? Because when the cluster redirects a frame, so the cluster, say you have some kind of asymmetrical routing, and the frame gets to this cluster member on the left side, but the connection is owned by a cluster member on the right side. So the cluster member will just flip it across CCL, but it flips the entire frame. So if you had something like MAC address BACD, the cluster member flips the frame which was going from B to A to this side. There is no B to A here if you didn't meter the MAC addresses. So absolutely make sure you always meter them, so this way, even if you have redirection, the frames actually get to their destination. That's very important in this particular scenario. So that's all great when you have one subnet per data center. But in recent times, actually not so recent times anymore, everybody wants to extend their inside subnets across multiple DCs. And you have virtual machines which travel between different data centers in real time. So how do you figure where this particular workload is at any given point in time? It used to be that the IP address tells you exactly where things are, but nowadays, well, the IP may be here, and now we may migrate it here, and now today, IPs travel between on-prem and public cloud as well, right? So there is a protocol that Cisco came up with called Locator Identifier Separation Protocol, where the locator place is separate from the identifier or the IP address. So how does it work? Okay, so say you're sitting on campus, right, in your corporate campus, and you want to reach a certain IP address, your application in a data center, right, your database application. So you just, put the IP address, and the network tries to connect you. So the packet starts traveling to this particular IP address, gets to your edge router. And you have two data centers, DC1, DC2. So your edge router, if it's Lisp enabled, what it does, it asks this Lisp mapping server, hey, I'm trying to reach this IP, where is it at again? And for now, we just assume that this Lisp mapping server knows exactly where things are and says, yeah, I know that. This IP is in DC1 behind router A. So this Lisp speaking router encapsulates this frame into Lisp payload and sends it straight to DC1 router A. And of course, it's a new protocol, so we're going to be cool. We're going to come up with some new terminology. So the campus router is called the ingress tunnel router, ITR, and the receiving router, router A, is called the egress tunnel router, or ETR. So ETR gets the packet, decapsulates, and sends it to its local segment to reach that VM. Oh no, you decided to migrate this VM from site 1 to site 2. So now that routing is no longer optimal. So what to do? So when this host VM migrates, it starts generating packets toward its first hop router, FHR. And that first hop router tells its edge router, and now we call it XTR because it's both ingress and egress tunnel router. Right? We love creating new terminology, don't we? It just sounds so cool. So we have ITR, ETR, collectively XTR, and FHR, first hop router. So it tells this edge XTR, hey, we just got this new workload at our site. And so this XTR will tell the Lisp mapping service, hey, this IP address is now behind router B in DC2. So the mapping service updates the campus router saying, hey, this connection you established for DC1, no more, send it to DC2. And the connection flips, and now you have much more optimal routing. So why am I going through all this DC-centric complexity? Well, we actually integrate, we as an ASA and FTD clustering, we actually integrate with Lisp. So what we can do, we can detect this operation, we can detect the vMotion and the fact that the first hop router at the new site signaled the XTR that the workload moved, and we can automatically move the associated stateful connections to the new owner. So that's why you set up the site ID. So each site knows that the local connections can be moved to a different site, and then you inspect Lisp on the default port, and then you select which connections are migrated automatically. So you may not care to migrate every single connection, right? You may care only about certain applications, so you have the flexibility of setting in there. So this is available on ASA CLI, and on FTD you have to do this through FlexConfig, but it works. So for north-south clustering, like I said, it's the easiest, most commonly deployed scenario. You can even shift your connections dynamically with the workload. However, a lot of folks, a lot of my customers want to deploy a cluster as the first hop router, not north-south, but east-west. Right? I want my first hop gateway to be the cluster. And we thought, okay, well, back in the day, we thought, yeah, that's pretty easy. It works. We could do east-west first hop and routed mode. It actually works quite well because, well, we already have the same MAC address and same IP address on each cluster member, so that's cool. If the VM migrates, the same default gateway, all right? The inbound connections established at site 1, check, right? The virtual machine migrated to the different site, we can definitely accept packets to this VM through site 2, though there comes a little problem, right? So say this happened, right, and the new connections are now coming in through site 2. Traffic for existing connections still can come in through site 1 and go across the extended, so we are extending the subnet across sites on the bottom. So the cluster member, the original connection owner at site 1, can use the extended segment to reach the workload. That's all fine, but the switching technology creates a problem for us because now, remember, the cluster units have the same MAC address. So they will source frames from the same MAC address. So your switch at site 2 is going to get frames from the cluster member on site 1, and site 2 source from the same MAC address to the same endpoint. Well, it doesn't work. You cannot have the same MAC address coming in from 2 different ports. So you're going to have MAC address flopping in general unpleasantness in your network, and it will never work. So when we tested it, we were, okay, well, we got to do something about it, right? So the solution was we will introduce per site IP and MAC addresses. So in span port channel mode, for each port channel, for each cluster member, we will still have one global IP address and global MAC address, which is used to receive packets, kind of like HSRP, right? You get a global MAC address, a global IP address you use to receive packets as first hop gateway. But we will also have per site MAC addresses and IP addresses to source frames. So here, that's the global MAC address, and for each site, I'm going to specify what MAC address and what IP address the cluster members at this site will use to generate traffic. So if they want to reach somebody across a different site, across the extension, that's cool. They're going to all use a different MAC and IP address. Well, like, not so much IP address, MAC address. IP we do use for ARP, because ARP does not like when you mix different IPs and different MACs, so it's a one-to-one correspondence. ARP inspection on Nexus does not like that at all. But anyway, beside the point, right? You solve that problem of 2 cluster members coming in from single MAC by using per site MACs. Great. The only caveat in the east-west clustering is that dynamic routing is not supported. We can only do static routing. I came up for one customer, it took me a while, I figured out a scenario where you could actually do dynamic routing with BGP, and I'll talk to you about that in a few minutes. But for now, let me talk a little bit about OTV. So OTV is overlay transport virtualization. It's a Cisco technology used to extend data subnets at layer 2 across layer 3. OTV is a tricky beast, right? There's a lot of different nuances to it, and one of the most commonly encountered problem is the problem of silent hosts. OTV by default does not do unicast flooding. So if OTV gets a frame destined to a MAC address it doesn't know about, it's not going to send it to all the sites. It's just going to say, you know what, unless I know where the MAC address is, I'm going to just not bother and drop it. So the problem is if you have hosts which don't naturally generate a lot of traffic, other sites would not know about it because OTV will time them out. What's OTV's solution? Well, you could set the MAC address timeout for your OTV CAM table below your ARP timeout. So this way, every time there is an ARP event, OTV will relearn that host. So we try to help OTV from the cluster side, make it a little bit nicer, right? A little bit of a Cisco-on-Cisco integration you don't see as often as you'd like, right? So first of all, we help OTV by replicating ARP at all sites. If somebody at site A, some machine at site A workload ARPs for the cluster MAC address, when we reply out of all sites. This way, OTV will relearn that MAC address. It will see, okay, a frame coming into this workload, I will refresh the associated CAM table entry. But it was only partial, right? And it didn't really solve the problem of, well, cluster itself. The global MAC address does not generate frames, it only accepts frames, so our cluster becomes a silent host. So that's the feature. So remember I told you last year at Cisco Live Orlando, I talked to the customer who had this very problem, and we thought up a solution. So the solution is we will periodically generate an ARP, a gratuitous ARP, out of the cluster for the global MAC address. So that's coming in 6.4 this spring, and there's a command to configure it. So you can tell the cluster how often to generate the ARP. You could set it to 280 seconds, just a hair below the default 300-second MAC address timeout on the switches. So the cluster will always remind OTV that it still exists and it's there so it doesn't become the silent host. So that's pretty cool. Again, another example for east-to-west insertion. So an FTD cluster as the, or ASA cluster as the first hop router in a data center. Again, I'm not going to go through the fine details. It's just mostly for you to look at. So one call out is, again, OTV is still a tricky beast, right? OTV, on the extended segment, you still have to create filters to prevent the global MAC and global IP address of the cluster from leaking between sites. That's just classic DCI, right? Even if you take the cluster away, you still have to do that. So that's something you got to keep in mind. That's the big takeaway here. So on the cluster side, it looks big and complex, but all there is to it is the per site IP and MAC address configuration. I am using static routing on the Nexus side, so it's pretty simple. And this ugly blob here, that's what's doing the OTV localization. Just again, to give you appreciation for what our data center colleagues go to when they go through, when they configure OTV. You have to filter the global MAC address of the cluster and global IP between sites, because you don't want the host at site 2 from talking to a cluster member at site 1 and vice versa, unless something failed in site 1. And those filters have to be removed manually if there is a failure. So like I said, we only initially supported static routing with intersite clustering east-west, but then I figured a way to do BGP in this BGP on the outside in this scenario. Again, I had a customer and they were going through a deployment, and we kind of had to sit down and figure out how to solve this, and we tested it and it worked, and it was cool. So here you have the east-west cluster, right? The same deal right here. You have on the inside, I'm not showing the inside, but on the inside you have per site IP, per site MAC, you have OTV, all that good stuff. On the outside you got none of that. You have OTV, but no per site IP, no per site MAC. So on the outside is just a global MAC and IP business as usual. And you localize HSRP on the upstream router side. You have the, obviously as you see, you have the same HSRP next hop address, so you have to localize those in OTV, make sure they don't overlap. So OTV blocks all that. So now, like I said, in clustering, only the master is establishing routing adjacencies. So the master will peer with the local side, that's all easy, right? Now the trick happens when the master needs to peer with the router on the remote side, because we localize, right? So the remote side can only reach the local cluster member right here. So it's going to send the BGP hello to the local cluster member. BGP is a centralized protocol. If a non-master gets this packet, it will always redirect to the master through CCL, and the master will conveniently reply directly to the extended segment. So you have this triangular BGP session establishment, but it works. They will peer on both sides. And so now, when the inbound connection comes in at site 2, well, site 1 is obvious, right? It's the local master. At site 2, the local cluster member at site 2 replicated the entire routing table from the master, so it will direct it correctly. But when the outbound connection comes here, there is a problem, because BGP by default will advertise the next hop as the burned-in address, configured address. So it's not going to advertise HSRP, and since the burned-in address of the router at site 1 is different than site 2, you may have that triangular routing. You don't want that, right? So what you do, you create this nice route map on the cluster, which says whenever a route comes in from any one of those routers, we'll rewrite the next hop address to the HSRP IP address. So this way, each site will always direct traffic to its local router's HSRP address and never do this triangular routing. So this actually works. And it's pretty cool. This is my opinion. So I promise you a very brief discussion with ACI Anycast services. So ACI Anycast services was, again, a feature we co-developed with the ACI team. They came to us and I said, look, it'd be really nice to make intersite clustering work in ACI, multi-pod and multi-site eventually. But the problem is ACI does not like when the cluster, the multiple same IP addresses across the fabric. That's how clustering works, right? So we worked out this feature, which what basically it does is you configure the global IP address of the cluster in ACI, and you say, this is my Anycast service gateway. And what it allows ACI to do, it enables ACI to say, okay, I will allow this IP address to show up multiple times in the fabric, once per pod. And whenever I get traffic to this IP address, I will direct that traffic to the closest pod to the workload. So if you have a workload at pod 2, when this workload generates traffic and you want the firewall to be first scope gateway, ACI will recognize the IP and MAC of the cluster being the destination, and it will say, okay, I'll take this frame and I will deliver to the closest cluster member to this particular workload. And if the local cluster member is gone, I will direct it to the second closest pod. So you don't have to do per site IP, you don't have to do per site MAC. It's literally as simple as configuring the global IP and MAC and ACI and the APIC, you plug it in, and it just works. And it's really cool. And for now, it's only multi-pod. Down the line, we'll support multi-site as well. The main caveat there is the latency requirement, because ACI wants to go big. They want to be one DC on East Coast, one on the West Coast, and we're going to align the latency requirements a little bit. So last feature in connection to inter-site clustering is the directory localization and redundancy. So directories are always selected across the entire cluster, and you don't have control whether they are created at the same site or a different site. So what directory localization helps you to do, it will help you create a local directory to each site, even if the cluster hash logic created a directory at a remote site. Because always talking to the remote director is expensive. Again, DCI bandwidth and latency, so you want to be local, right? So that's the command you use to always create the local directory, local backup at each site. And the site redundancy does the opposite. It says, well, look, if my entire site goes away, I want connection to survive. And if I want connection to survive, I better have a remote director. So it does the opposite. Like I said, it always creates a director at a remote site, and this way you always have redundancy even if the entire site crashes and burns. So that's inter-site clustering. Again, I get it's probably the most complex non-security type of talk or the section of the talk you've heard in a while. But again, it helps us appreciate when we go and deploy multi-site data centers. And I have tons of customers doing that, by the way. Multi-site DC. I have a large gaming company doing it across 8 sites. I have healthcare companies doing it across 4 sites, right? Those deployments are pretty common. So as you get requirements for doing something like this, at least you are a little bit better prepared on how to tackle those. So in conclusion, we talked about quite a few things, right? Some best practices I want you to take away. So like I said, clustering now does not require a special switch. Just make sure it adheres to the requirements. Always try to use LACP for your port channels for both data plane and CCL. On CCL, again, always set the MTU to 100 bytes above your largest data interface. A #1 problem people run into. And also, second most common problem is that CCL is on per appliance basis, not spanned across the entire cluster. You can simplify STP conversions, enable features like NSF, non-stop forwarding, and graceful restart. Helps your dynamic routing not impact your traffic flow on failure. And then try to reduce asymmetry of traffic as much as possible. With something like NAT, it's pretty much impossible, but without NAT, firewall on a stick is a very popular design to help that. So like I said, WebEx Teams, I will look at questions right after the session, make sure I answer all of them. Session survey, Luke's standing right there looking very nervous. Luke is our session group manager, and we all live and die by our scores. So if you like the talk, 5s are appreciated. If you want to add some comments, we always read all those comments and make sure we do whatever we can to improve upon the session for next year. So again, please fill that out. We still have a few days left. Have fun, enjoy the party, and I hope we see you next year.